Hello everyone, welcome to this lecture on air transportation. This topic actually is a little bit futuristic in nature. It doesn't talk about the transportation systems which is currently available and established, which is what we are used to, the topic of airlines, airports, air traffic management, etc. This goes little bit into the futuristic look at what we are expecting to see in the near future. Today we will look at how one can have sustainable aviation using buoyancy engineering. So, let me start by first defining what is sustainable aviation. Sustainable aviation actually means an attempt to meet today's aviation requirements and also of the near future without compromising the resources available with us for the future. So, without compromising on the resources for future generations, we should meet the requirements. So, the steps which are generally followed in promoting or achieving sustainable aviation, they focus on reducing three basic things: reducing the carbon emissions through the use of less polluting fuels, trying to achieve propulsion using non-renewable resource use reduction. That means, we have these fossil fuels which are used today for fueling the aircraft. Can we try to achieve the thrust requirements using renewable resources or by reducing the use of non-renewable resources? And another aspect which is very important is to reduce the noise pollution, because that is becoming a serious issue as the populations increase, as the aviation activity also increases. More and more noise and pollution near the airports is causing a huge dent in the quality of living of the people in the vicinity of the airports, and that also is hitting its sustainability. This attempt of achieving sustainable aviation involves innovations in fuel, such as the use of sustainable aviation fuel or blended fuels with naturally grown biodiesels, or improvements or innovations in operations. And also we can achieve this by design of newer and newer aircraft, new type of aircraft, and also improving the design of the current aircraft. So, today we are going to look at the sustainable aviation by design or usage of a new type of aircraft, and that is aircraft based on the principle of buoyancy. So, what is buoyancy engineering? Buoyancy engineering represents creative problem solving by exploring buoyancy for lift generation. Traditionally, we generate lift by ensuring a minimum relative velocity between the flying object and the ambient air. But for that, you have to use a propulsive device to move this aircraft at certain minimum speed. But what if we can use buoyancy as a mechanism to overcome gravity? Then you do not have to fly at any speed, even at zero speed or stationary you will be able to get. So, buoyancy engineering basically means application of Archimedes principle, which, as you know, acts on either partially or fully submerged body. It says that the upward force that is acting on any body which is partially or fully submerged is equal to the weight of the fluid displaced, and it is also applicable for a fluid inside a fluid, not necessarily only a solid body in a fluid. Now, there are many applications of buoyancy engineering. One of them is the hot air balloons, where we enclose the envelope of the balloon with hot air generated by using some burners on the bottom, and hot air has a density lower than the ambient cold air, and therefore you start getting buoyancy. Then you also have submarines which work on the principle of buoyancy to come up to the surface and to go down below the surface, so that they are less detectable. And the third application of buoyancy engineering is airships, which are aircraft that are operating, and today we will talk about airships. So, airships belong to a family of systems called as lighter than air systems, or in short we call them as LTA systems. So, what are lighter than air systems? Basically these are buoyant aircraft or systems that use any lighter than air gas or any gas whose density is less than that of air, and the purpose is to overcome gravity without the need for relative motion. These are very efficient non-wing based lift generation techniques because they can generate lift even when they are stationary. There are three most common types of LTA systems, and then there are many hybrids of these types: hot air balloons, aerostats and airships. So, hot air balloons, as I mentioned to you, are platforms which take you from here to somewhere depending on the wind direction. They do not have any directional control. They just use hot air to generate lift and to overcome gravity. Aerostats are platforms again, but they are unpowered. So, they only have on their rear some stabilizing surfaces which allows them to not move too much with the changes in the wind direction, and they are unpowered. So, they cannot go anywhere. They are connected with a cable to the ground and tethered. And then you have airships which are like an aircraft. They have a 3-axis directional control. They are powered, and to some extent using the power of the power plant, they are able to overcome the winds and fly in the air. So, today we will not discuss the aerostats and the hot air balloon because they are not relevant to our discussion. They cannot be used for transportation from a desired location to another desired location. Balloons will go wherever the wind takes them, and aerostats cannot go anywhere. Airships can definitely travel from point A to point B to a large extent. Now, let us do a brief comparison between the two families of systems, the lighter than air on the left hand side and the heavier than air on the right hand side. Let us first look at the heavier than air system because they are very popular, people know about them. Okay. They have two fundamentally good features, which is that they are fast and they are less susceptible to weather changes. But there are also many negatives of heavier than air systems. Primarily they require certain minimum relative speed to fly to generate lift, otherwise they will fall. They are very much inefficient as far as fuel is concerned. The whole world is grappling with the consumption of fossil fuels to support the current aviation, and they are complex. Anyone who has made an aircraft will realize that these are not simple to make, they are very, very complex. On the other hand, the lighter than air systems, they not only have dynamic lift when they move because of the relative motion between them and the ambient air, when they are stationary they also generate lift because of buoyancy called as the aerostatic lift. They are highly fuel efficient. The amount of fuel that they consume is a fraction of what is consumed by a heavier than air system, and in general they are less complex to operate, but they have these two main fundamental flaws. One is that they are slow, and other is that they are very much susceptible to weather changes, very much susceptible. Because of these two major drawbacks, the three positives are overcome and you do not see them very often. They are not yet very popular, they are a niche area of application, but they are slowly emerging as alternatives to the heavier than air systems for certain transportation requirements, and that is what we will study today. Now, the LTA systems are based on LTA gases. So, what are the LTA gases? If I ask anybody, they will immediately say, okay, any gas or mixture of gases whose net density is less than that of the ambient air can be called as a LTA gas. The two principal gases which everybody knows are hydrogen and helium, which under the normal temperature and pressure conditions provide you a lifting capacity of approximately 1.1 and 1 kg per cubic meter, which means if you take a balloon of hydrogen which weighs, let us say, 135 grams, and if you put in it 1 cubic meter of hydrogen, because the self weight is 135 grams, the net lift you will get will be 1 kilogram. Okay. Similarly, helium will also give you slightly more, around 7% more lift, 7% less lift compared to hydrogen. However, there are many other gases also which are LTA. So, there is methane, there is ammonia, there is water vapor, acetylene, carbon monoxide, all of them are lighter than air. Okay. But the problem is, if you look at the lifting capacity, it reduces drastically as you go down in this list. So, the best is hydrogen with 1.135 kg per cubic meter, and in this list the least capable is carbon monoxide, which is only 0.06 kg per cubic meter, which means you will get only 60 grams of lift by a cubic meter of carbon monoxide. Therefore, it is practically of no great use to us. Let us have a look at how airships can give you sustainable aviation and how sustainable aviation can be achieved using airships. Airships, they reduce the fossil fuel based thrust dependency by using buoyancy for generating the major part of their lift. They enable very low energy hovering and vertical landing, which is not possible with many of the HTS systems unless they consume large amounts of fuel like helicopters or aircraft with vertical takeoff and landing, who can operate vertically and also hover, but they consume massive amounts of fuels in that process. Airships can do the same thing with much lower energy requirements, and they are quiet because their engines are smaller and therefore they are quiet. Since the fuel consumption is also much lower, they are also have low emissions. So, both on the emission front and on the noise front, airships score over aircraft, and therefore they are very powerful candidates for sustainable aviation. Now, as far as you look at the transportation of passengers, we are not looking at airships as a means for transporting passengers on a regular basis from A to B, because the dispatch reliability is very low, primarily because of the susceptibility to the weather conditions and very large size and slow speed. But if you look at cargo transportation, it opens up a new opportunity. So, today cargo can be transported either by a ship or by a train or by a truck or by an airplane. These are the four ways of transporting cargo, especially over long distances, intercontinental distances or large distances, right. Now, if you plot a graph where you look at the average cost in dollars per ton mile versus the vehicle speed in knots, a knot is approximately, 1 knot is approximately 1.853 kg meter per second square. So, roughly you can figure out the value from there. Notice that ships are the slowest but the most cost effective. Airplanes are the fastest, but they are the most expensive per ton mile. And notice the graph is actually logarithmic in nature, it is not a linear graph. So, you have 10, 100 and 1000 knots. Trains are faster than the ships and marginally more expensive. Trucks are much more expensive and little bit more faster. They are faster because they can use the existing roads, whereas trains are going to use special purpose rail. Then you have airplanes which are very fast but also very expensive, and there is a huge gap in between. This gap is where airships fit in. They push themselves in the gap that you can see here. Okay. So, if you look at airship in a steady flight, you will see that there are these four forces acting. There is a lift force because of buoyancy, which overcomes the weight, and then there is a drag force which has to be overcome by providing the required amount of lift. Now, the volume of the gas that you have inside this big envelope is the one that gives you the buoyancy with no additional energy, and the single formula that captures the dynamics of lift generation in a buoyant system is mentioned there. You can notice here that you have these two things. You have the volume of the envelope and you have the difference in the density of the two gases. So, let us say you would like to have more buoyant lift. One way is to increase the volume of the envelope of the airship. With increased volume, you also have a problem of increased weight because there will be more material used. So, there is a limit to how much benefit you will get. The other option is that you reduce the density of the gas inside or the gas mixture inside. Now, if you use hydrogen, then you do not have any further scope of improvement with any naturally occurring gases. So, you have reached the limit of the least dense gas. The other option is rho A, that is the density of the air outside, which can be increased if possible. Now, how do you increase the value of rho A? One way is you fly at lower altitudes, because at lower altitudes we know that density of air is more than at high altitudes, and also fly in cold weather, because we know that cold air is heavier than hot air. So, if you fly at low altitudes in winter, you will get the maximum possible lift from a fixed volume and a fixed LTA gas. So, these are the only three things available to you to increase the buoyant lift of an LTA system. Now, historically airships were ahead of the aircraft, and if we trace their development from the 18th century till last 2 decades and the current times, you will notice that several years before, the Wright brothers, the Montgolfier balloon established that LTA systems can be used. In the 19th century, when the Wright brothers were struggling to make their aircraft really make operational, there were people like Santos Dumont from Brazil who were flying airships regularly. And then during the 20th century, there was a huge amount of development in the airship technology, but the aircraft technology was slowly catching up. And then because of a series of accidents that took place in late 30s, early 40s, the airship technology was into hibernation till it was revived in the post-war period by some interesting projects, and the outcome of that project eventually was a blimp. And then you have in the last 2 decades lots of developments, and recently there have been attempts to use airships for exploration of outer planets like Venus, and there are proposals to look at what is called as hybrid airships, which have some additional interesting features. So, the whole landscape has now emerged. So, after about mid 80s to 90s, interest in airships is being revived, and in the last 10 years there has been tremendous interest, as we will see. Like an aircraft, an airship has similar components. There is a gondola where you put all the payload and the items. In this case, we also put the propulsion system on the gondola. You have this large envelope in which you put the LTA gas, and then you have control surfaces. The main difference, as you can observe, is that the gondola, which is equivalent to the fuselage of an aircraft, is much smaller in dimension compared to the lift producing device, which is the wing in the aircraft and the envelope in the airship. Also notice that you have more area of control surfaces in the case of airships compared to aircraft. For example, aircraft normally have only one vertical fin, but here you can normally see 2 vertical fins. That is because airships fly at low speeds, so they need large areas to provide the yawing moment to balance out the instability in yaw. There are 4 types of airships based on the structure that is used to construct them. On the top left is the rigid airship, which was used in the past and is coming back in a big way today in the future of the large size cargo airships. On the bottom you have a non-rigid airship which has got no internal structure. It only has an envelope which is maintaining its shape by the internal overpressure. Then you have a compromise solution called as a semi-rigid, where there is an internal rigid structure like you have in the aircraft. You have these frames and the longerons, but the envelope is flexible. Okay, so that is called as semi-rigid. One of the most successful airships flying today is Zeppelin NT, which is a semi-rigid construction. And the bottom right is a hot air balloon which is masquerading as an airship. It is a hot air balloon in the shape of an airship, but it can't be used for any serious work except promoting products like KitKat or flying around for personal adventure. It cannot really be used for anything very serious or transportation purposes. Okay. Now, what is the unique selling proposition or USP of airships? Why are we talking about them? First of all, they are able to operate from open fields. They do not require a dedicated runway or an airport. So, that makes them available to operate from remote areas. They have extremely high endurance capability compared to the aircraft, because they use much lesser fuel compared to the aircraft, and therefore, when an aircraft can fly up to maximum 18-20 hours non-stop without refueling, airships can fly for much longer time. 50 hours has been recorded, 52 hours has been recorded quite routinely on airships. Airships allow stationary and low speed flight, and because of that you can have onboard surveillance systems to operate in high clutter environment. Okay. Then it will give you large cabin space and low vibrations, which will reduce the crew fatigue as compared to the aircraft. The large cabin space is available because you already have a large envelope, so you can put a large cabin below it. This is a vehicle that gives you low noise, low environmental pollution, and it can be made unobtrusive by camouflaging it with the background. Okay. And there are many applications of airships as an aerial platform, and we always say that the applications of airships are limited by your imagination. Okay. There are many uses. Let us have a look at some current application of airships. The most common application of airships in the world today is for these two activities, for product promotion and for advertisement. Then there are obvious applications in aerial observation and surveillance. Many applications, especially the Zeppelin NT airship of Germany, is used for tourism and corporate hospitality. Then there are some very innovative applications, such as the use of airships for removing the landmines in this airship funded by the UN called as the Mine Seeker. I would encourage you to go and search the website mineseeker.com to have a look at what was done to take care of the landmines which were left after the Kosovo conflict. There is also a recorded application of airships for several applications of law enforcement, such as during the Olympics in Athens and Olympics in Atlanta. Now, we will look at sustainable LTS systems and how they can be applied. We can use them for surveillance and monitoring. We can use them as airborne communications relay to provide communication links in areas which are not connected. We can use them for cargo transport in remote areas. This is the principal application of LTS systems for sustainable aviation in the future. And also one can use them for tourism and short haul passenger travel. So, if you look at airships for cargo transport in remote areas, these are two prototypes which have successfully flown. The Basi cargo airship prototype, which was flown in Canada, and the Pathfinder 1, which was flown in San Francisco Bay. Both of these, please note, are only working prototypes. Then there are certain concepts which are under development, such as the flying whales shown on the bottom and the Atlant concept of Atlas LTE shown on the top left. These are under development and we will hopefully see them flying very soon. When we look at cargo transportation, large volumes of cargo transportation, the rigid airships become a very promising category. Why rigid airships? Because they have the internal framework to distribute the loads and to bear the stresses which are inevitable when you transport large weight of cargo, which are heavy and also concentrated, such as this image shown here. Then rigid airships also have better resistance to the weather, which is a problem that many semi-rigid and non-rigid airships face. And if you have to transport cargo over long distances, you will need better weather resistance. Then they also have a scaling advantage. Okay? Using the square cube law, the moment you make them larger, they will be much more productive and efficient. Because as we all know, when you increase the linear dimension, the area goes up by square, but the volume goes up by cube. And the lift that you get from a buoyant system is proportional to V cube, whereas the weight of the system is proportional to V square. So, there is a straightaway example advantage in scaling the airship. The lift to weight ratio increases when you make airships larger. So, when you want to transport huge cargo containers, larger airships are definitely much better. Also, the rigid airship is also going to have lesser gas leakage, because the gas bags will be inside a solid structure, not exposed to the vagaries of the outside world. Plus, because of the rigid structure, you will have higher redundancy. So, the structure can bear more, the structure is much more efficient and redundant. Modern innovations have made this rigid cargo airships also a very promising candidate, such as the use of carbon fiber composites for the skeleton, which gives you high strength to weight ratio, using Kevlar reinforcement and titanium hubs at points which are supposed to be highly stressed. And there is a huge amount of research in the development of specific material for gas tight fabrics which are lightweight and also capable. So, airships are finding their place in the speed, cost and supply chain. So, there is a mid-range niche between the slow cheap sea and the fast expensive air freight. They are able to find a niche. As I showed you in the previous graph, they are filling that gap between the aircraft and the sea. Now, the cost in rupees per ton kilometer for trucking increases much faster with distance than for airships, and they have lower dependence on infrastructure as compared to other modes. So, if we compare roughly the parameters related to transportation of cargo over long distances, okay, by shipping, by rail, by truck, by airship and aircraft, you can notice that, as I mentioned earlier, shipping is going to be the least expensive, ranging from 0.85 to 2.5 rupees per ton kilometer. These numbers were taken from study in the literature by various agencies. So, it is not that these have been already tried out, these are all predictions. Okay. Rail transportation entails around 3.5 to 7 rupees per ton kilometer. Truck is more than that, airships are in between that and the aircraft. Okay. The speed of the airships can be of the order of 80 to 150 kilometers per hour, which is 10 times lower than that of the aircraft, but of the order or slightly better than that of the truck. Remember, we are doing point to point transport in airships, so you do not need to really follow the road, especially in hilly areas where the roads can be highly curved. So, if you look at the comparison, you find that there is a niche between the truck and the aircraft that the airships can accommodate. Now, where are the airships making a difference? What applications? Remote area logistics, areas where you do not have runways, we do not have airports, we do not have rail tracks, we do not have roads. These remote areas where we want to build infrastructure and we want to provide logistic support, that is where airships can be used. Logistics required by the military, which work in newer and newer areas. Some post-disaster areas where you need to provide support to relieve. If you want to carry oversized loads such as these large blades of the wind turbines to remote areas. If you want to transport supplies and equipment in very, very cold and inaccessible areas where you do not have the roads, then using airships one will have greener skies and provide sustainable transportation system. Here is a comparison of the greenhouse gas emissions with various transport modes. Cargo and rail have a very low value, but a heavy ground vehicle and vans, they have higher value. So, some studies were done by us to find out if we use conventional or existing old airships, like there is a very nice prominent airship called as Macon, whose data is available. It was used many years ago in the early 30s in the US. Suppose we take the value of Macon of that time, it is compared to a diesel van, but if you use modern gasoline engine, it reduces. If you change modern diesel engines, it becomes much better, and if you use electrical engines, it can also further be improved. So, if an aircraft, for example, generates about 1647 grams CO2 per ton kilometer, grams CO2 equivalent per ton kilometer, the airships can give only about 13, and if you use electrical airships it can be only 4. Okay. So, you can see the tremendous improvement, about 400 times lower emissions as compared to an aircraft. Okay. Now, there are many modern giants under development, and let us before we close down, let us quickly look at some of these promising configurations which are under study. The first of them that comes to our mind is the Pathfinder 1, which recently had successful flight, and they are planning to develop the airship as a 14-seat passenger aircraft plus 28 tons of cargo. Then there is a company that actually deals with supply of hydrogen to remote areas. They have proposed a concept called as a H2 clipper, which will only be used to transport the gas. It can carry about 150 tons as per their expectations over around 1000 kilometers, and equivalent to 35 shipping containers in one load. Okay, very promising. Then you have Flying Whales, which is a company in France which looks at transportation of 60 tons of cargo, maybe larger ones in the future. They are coming up with the design of a rigid cargo airship. Atlant 300, about whom I spoke, is another airship under development with multiple number of engines, multiple configurations. They are aiming to carry 165 tons to a 2000 kilometer range, but a very large vehicle with 311,000 cubic meters. Russia also is developing some concepts of lenticular airships for transporting huge amount of cargo in remote areas at high speeds over long distances. Then there are also proposals for carrying 250 tons using a hybrid configuration, such as the one ML868 from Worldwide Ores Corporation. Okay. Then this is a prototype which has already been developed and it is under testing. It is called as a Dragon Dream. The path ahead is full of challenges to be overcome. Buoyancy control is not easy, especially when there are large changes in the weight. Designing a structure which is very lightweight but very rigid is also a very challenging problem. Airships are new, their knowledge base has been lost over the years. We do not have data about the historical airships to that extent, and also today the information is not so easily available. So, estimating their total empty weight also becomes very difficult. Moving and securing very large airships from the ground will require infrastructure on the ground, and it will require some development of tried and tested operating procedures. Then one hard nut to crack is certification and regulations, because this technology is not really very prominently available. So, there are very large amount of doubts and questions regarding its viability, and the new designs which are being proposed, they do not happen overnight. They require a lot of testing, justification, so that they can be proved to be compliant from safety. But despite these challenges, it is very clear that airships do offer some unique capabilities for transportation, especially large volumes and weights of cargo. They have the advantage of significantly lower environmental impact because of the much lesser fuel consumption. They aim to fill a gap between the trucks and the aircraft in the transportation spectrum, but with all that, the bottom line is that if we are able to overcome the significant technical, operational and regulatory challenges, then these giants will definitely redefine the way we conduct global logistics. Thank you so much for your attention.